Hello and welcome back to Calculus 2, section 8.4 on trigonometric substitution. So at this point, we are going to take integrals that have functions without trig and turn them into trig to solve the problem. Before we do that, I am going to review some of the basic trig rules so that we can learn this a little bit different than what the book has to offer. In the book, they're asking you to memorize 3 different cases and when each one applies, and then to memorize 3 formulas and 3 procedures, and it's just too much. How about we just learn one procedure that applies 100% of the time? That's much better than worrying about 3 situations and 3 formulas and 3 procedures and all of that. So I figured this out when I was a student, and I've never looked back to memorize the cases. Now, if you want to memorize cases from the book, sure, you can. Right? They will get you the same place. So we have a right triangle, and in right triangle we're going to have angle theta. This is going to be the hypotenuse, usually labeled as C, and then 2 legs, we can call them A and B. What we must know is that sine theta is opposite over hypotenuse, so that's A over C. Cosine theta is B over C, and tangent theta is A over B, looking at this picture. Now the cosecant is a flip of sine, so that's C over A. Secant theta is a flip of cosine, which is C over B. And finally, cotangent theta is B over A. And we also need to know the Pythagorean identity, which says A squared plus B squared equals C squared. So this is the review of trig that you guys need to set up your trig substitution. Now, the method that I'm going to show you is fairly simple if you know a few things. First off, you can come up with C is equal to square root of A squared plus B squared, right? If you just take a square root over there. A is equal to square root of C squared minus B squared. And B is equal to square root of C squared minus A squared. So we just need to realize something about these 3, and we're good to go. Note that if there is a minus sign under square root, C is first. And over here, plus under square root, both are legs, A and B. That's how we are going to know, when we see a problem, that's how we're going to know where to assign values in a triangle. Now, this doesn't make a lot of sense until we do an example, so we just have to go and do example right away. One of the best examples would be to integrate, figure out the area of the circle, and you can only work on 1/2 of the circle because circle is not a function and so on. So let's say you are supposed to integrate square root of 9 minus x squared dx. Right? Why are you doing this? Because I mean, if you integrate from -3 to 3, you will find the upper half of the circle area, and then you multiply that by 2 to get the bottom part as well. So that's the motivation to do these kind of things. But we are interested now in a process of figuring out trig substitution. So here's an example. And now, if you take a look at your choices over here, this example matches the bottom 2. It doesn't matter which one. It just matches the one with a minus, right? Which means because it has a minus, 9 is a 3 squared, 3 is a hypotenuse. That's the important part. So I need to populate this triangle so I can write my trig functions, right? I need to populate this triangle. So when I look at this problem, I need to know which one is the hypotenuse, which ones are legs, right? So because there is a minus sign, and this is what the red stuff over here means. If there is a minus sign under the radical, then hypotenuse C is the first value. So I know that this is 3. Because this is 3 squared. C squared. C squared, right? And now, this is any leg. It doesn't matter which one. You can put x here, or you can put x there. It doesn't matter. And if you don't like it, as you start calculating, you can swap them. It doesn't matter. So let's say x up there. Now, if you use Pythagorean theorem on this triangle, you will end up that this is 9 minus x squared, which is exactly the thing you have over there. And here is a trick. You will create 2 trigonometric functions, including sides, but one of those sides has to include the number. So one of the 3 sides will always be a number. One of the sides. That number can be on any of the 3 sides. You will create your trigonometric functions always involving a side that has a number in it. So now I have the red one. Well, what's the red one? This is opposite over hypotenuse. Well, that's a sine, right? So sine theta is x over 3. From there, I can write that x is equal to 3 sine theta. And since we also need to replace dx, we will also differentiate this to get 3 cosine theta d theta for our substitution. So all I did is for the red pair, I wrote the trigonometric identity opposite over hypotenuse, which is sine, and then I solved that for x. And when I solve it for x, I differentiate x as well because I need dx. I need to replace dx as well. Then I go in a blue and I say, well, that's a cosine. Cosine theta, as you can see, is equal to the square root of 9 minus x squared divided by 3. Adjacent divided by hypotenuse. Now I am recognizing that I need the square root. So I'm just going to solve for square root because I will be swapping that as a unit. And that's 3 cosine theta. All I need to do now is to swap all of those things in the integral. So integral, instead of the square root, I am writing 3 cosine theta. And instead of dx, I am writing another 3 cosine theta d theta. So just to write the little legend here or whatever, this is the square root of 9 minus x squared, and this over here, the whole thing is dx. So as you can see, I have 9 integral cosine squared theta d theta. So I have transformed the integral from the top, right, the one with the square root. Guys, there is nothing you can do over here. You can't use u sub because you need an x in front, right? So you can't use u sub. The by parts doesn't work. Right? Nothing works. You can just stare at it, right? But if you use this clever trick where we say, okay, so this is like a Pythagorean identity, so that's going to be my hypotenuse because it's a minus. Hypotenuse is always first. You go to the procedure and look what you got. You got the integral that you can actually work with. Yeah, it's a trigonometric integral and you have to suffer through that, but at least the problem is possible, right? Because in the original case up there, nothing you can do. So this is now going to be 9 over 2 integral of 1 plus cosine 2 theta d theta, which gives us 9 over 2 theta plus sine 2 theta over 2, everything plus c. You cannot leave this in thetas. The problem asks for x. So now you have to break this down. We're going to do 9/2 theta plus. And now this is where I told you that double angle formula would work. So you have 2 sine theta cosine theta divided by 2, and then plus c. These guys cancel. So what is this now equal to? 9/2. For theta, you can use any of the 6 inverse functions. Generally, people use the first one you run into. So inverse sine of x over 3 is just fine. Inverse sine of x over 3 for theta. Plus, now, sine theta. Well, sine theta is given to you. It's x over 3. Just need to scroll. And cosine theta is given to you in blue, which is root 9 over 3. Root 9 minus x squared over 3 plus c. And just clean it up if you need to. We can apply 9/2, or we don't have to. Let's leave it. Sine -1 x over 3 plus 1 over 9 x square root of 9 minus x squared plus c. Yay. We were able to do this. Now, all of the problems, and I think they assigned about 70 or 80 of these in the homework over here, they all done this way. Doesn't matter what they have inside, as long as so you don't have to memorize cases. You guys have 56. 56 in the first batch, and then there is another batch of 10 later. So that's like 66 problems. That are just straightforward. There are word problems and other things, so over 100 problems available. Let's take a look at another problem. All we need to do here are, if you are understanding the way to put that triangle together, the rest is not supposed to be difficult. But then, you have your talents in making non-difficult things into impossible, so nothing I can do about that. Let's take a look at another example. Say, it doesn't really matter, they're all the same. How about problem 26? It's the square root of 2 to 2. Square root of x squared minus 1 divided by x dx. If this was flipped, root in denominator and x on top, it would be a u sub. And you would be done in one step. But it's not flipped, which is what makes it a trig sub. As soon as you see this square root of, it doesn't have to be a square root, but it's definitely easy to see when you do have a square root. So when you have a square root like this, that immediately screams Pythagorean theorem, and then you can set up the triangle trig substitution, and you're done. So we create our triangle, we put a theta, and again I have minus sign, which means, what's my hypotenuse? X. X is the hypotenuse because x is first. Again, I'm going to go back to those blue, look at those blue roots. Anytime you have a minus in a formula, c squared is first, which means hypotenuse is first. So we have another problem with the minus sign. Therefore, hypotenuse x is first. Now, where are you going to put 1? Doesn't matter. So, put it here, which will immediately make the other one to be the square root. We have the red pair and we have the blue pair. Let's go with the red pair. Red pair is going to be a sine function. Sine theta is equal to 1 over x. From there, x is equal to 1 over sine theta. And 1 over sine is what? Very good. Cosecant. Then we take the derivative to come up with dx, because we have to replace dx as well. So when you come up with a dx, the derivative of cosecant is negative cosecant theta cotangent theta. So we are going to have a pair now that's going to be cosecant cotangent pair. Let's see the blue one. See, blue one is tangent. Tangent theta is 1 over the square root of x squared minus 1. So now if you solve for square root, you get 1 over tangent theta. And that is what? So cotangent theta. 1 over tangent is cotangent. And I have all of my building blocks to do the substitution. Integral. The square root is given as a cotangent theta. The x is given as cosecant theta. And the dx is given as negative cosecant theta cotangent theta d theta. One of the cosecants drops, and all I have to do is to integrate negative cotangent squared theta d theta. Any ideas on how to integrate this one? We are not using power reducing here or anything like that. It's a very simple trick that you just need to see once in a lifetime at least. Can we integrate cotangent squared? Is it a basic integral? No. Which one is the basic integral? Which one? No. Tangent squared is also not a basic integral. Which one is the basic integral? With the squared. Secant squared, right? Or cosecant squared, right? What's the integral of cosecant? Squared. Integral of cosecant squared. What's the integral of cosecant squared? Yes. No. Negative. Negative. Negative cotangent. Negative cotangent. So we have to change this into, so cotangent can be written as cosecant squared theta minus 1 d theta. Then you can apply the minus in front, which will swap the order of these. And both of these are basic integrals. So what we have, I ignored the limits. Okay, we'll have to fix that. So 1 minus cosecant, so that's going to be theta, minus an integral of cosecant squared is, as you said, cotangent theta, and I have the limits, so I'm not going to put plus c. So what is happening with limits? Well, you can use any of these identities here to figure out the values of new limits in theta domain. So we need to go to theta domain. So if your x is root 2, this is 1 over root 2, which is root 2 over 2. Inverse sine of root 2 over 2 is 45 degrees, which is pi over 4. So pi over 4 on the bottom. And pi over 4 needs to go on every bottom when you had the thetas right? Pi over 4. And now when you plug in the upper limit, which is 2, what theta gives sine of 1/2? Pi over 6, great. 30 degrees. So pi over 6 is the upper limit. Now you have a smaller number on top as the upper limit, so you can swap that by changing the spots of cotangent and then theta, and then put pi over 6 and pi over 4. So now I have a cotangent of pi over 4 minus pi over 4 minus cotangent of pi over 6 and plus pi over 6. And there you go. Cotangent of pi over 4 is 1. And then cotangent of pi over 6 is going to be root 3 over 3. And you can simplify. I mean, you can't combine those roots with pi over 4 and pi over 6 at the end. So you might as well leave it here, but you can also compute, because as I said, cotangent of pi over 4 is not a big deal. Easy calculation. You cannot memorize that the minus sign under the radical means you have a sine cosine pair, because that has a minus, and we used secant, cosecant cotangent, and this one had the minus, but we had sine and cosine, right? Depends on the situation. Now, if you don't want to work with secants, or the cosecants and cotangents, in that case, you just need to flip the legs. Flip the blue circle. Remember how you can put 1 anywhere you want? If we are to put 1 on the bottom, then the square root would end up being on the side, and the whole calculation would change into a secant tangent pair. Now, it's always good to do that, to use secant tangent pair, because you don't have to worry about these pesky extra negative signs that pop up that you might easily forget. So if you are solving a trig substitution problem and you end up with having the cosecant cotangent pair, it is worth backtracking 2 minutes, right, to switch the legs in a blue circle. To switch the legs in a blue circle, and the equations are going to work out in that case to be secant tangent. Now, obviously, I'm going to challenge you to solve this problem at home, again, by switching the blue circle, and then you will see that you will have a secant tangent pair, and you will have the same answer. And it's a very good exercise, guys, because A, you're learning a very important skill, right, to swap it. B, you get to practice because you have the target answer, right? You need to get, if you plug this in decimals and your number in decimals, your problem into decimals, they should match. Let's do another one because we can, right? How about something with plus, because we haven't done any of those. 16, just fine. X squared divided by, ooh, this one is really cool. It doesn't have a square root, it has an extra square there. But you still have the form, right, of 25 and x squared, so we still can do this. Draw your triangle, and now what do we know? Because it's a plus, 5 and x are legs, right? So we can put x over here and put 5 over here, and then this one becomes square root of x squared plus 25. I know you don't have a square root in your problem, but we can deal with that. That's not a big deal. All right, time to create red and blue. So here, circle towards the number for red and circle towards the number with blue. Right, you can always create two equations so that at least one side is a number. All right, let's go red. That's clearly tangent, theta, being x over 5, from where x is 5 tangent theta, and immediately differentiate for dx because we have to swap dx as well, into 5 secant squared theta d theta. So now that we have this part done, we shift to blue. Blue is cosine theta, and cosine theta is 5 divided by the square root of x squared plus 25. We need to solve for the square root because that's what eventually needs to be in some form substituted. So square root of x squared plus 25 is 5 over cosine theta. And how can I write that differently? 5 over cosine.
5 secant.
5 secant. My function is tangent. I have a tangent secant pair. I am not allowed to have a cosine floating around, right? Because I am using secant tangent pair. Well, luckily, 1 over cosine is secant, so 5 over cosine is 5 secant. So I have a square root of x squared plus 25 equals to 5 secant theta. Now, here is the final issue. Do we have a square root in our problem? We don't, but we do have a square root here. I need to not just get rid of the square root, but also match it to be all the way to the second power. So what exponent do I have to put on both sides so that I can go all the way from square root into the blah squared? Which exponent? Fourth. Because fourth contains two squares in it. One square will knock off the root, and the other square will be the square that we need so that we can replace the whole thing. So we have to put this to the fourth power on both sides so that we can match the exponents and everyone is happy. So now I have on the left-hand side, I have x squared plus 25 squared. So I went from the square root all the way into a square by applying the fourth power. Now, obviously, on the other side, we have 5 to the 4. There's no reason to compute this because some of the stuff might cancel. So just leave it to the 5 to the 4th, and then secant to the 4th theta. So now we have all of the ingredients to work our substitution. My x squared is going to be, oh, I didn't do that. Yeah, x squared, I need x squared, which is 5 squared tangent squared. So the x squared is going to be 5 squared tangent squared theta. That's going to be divided by the blue one. And see how you have the 5 to the 4th now? They cancel. Secant to the 4th theta. And finally, I also have, for dx, I have 5 secant squared. 5 secant squared theta d theta. So you have 3 5s in the numerator and 4 5s in denominator. So that's going to work as 1/5. Right? You have 5 times 5 times 5. So that's 3 5s on top and 4 5s on the bottom. So 3 will cancel, leaving you with one of the 5s. You have 4 secants on the bottom and you have 2 secants on top. They also cancel, right? So when you cancel these 4, you're left with 2, and these are completely gone. So now the problem over here is much simpler. Tangent squared over secant squared theta d theta. So far, we were dealing with trigonometric substitution. Well, that part is done and done, right? The next is, hello, trigonometric integrals. We need to figure out the way to integrate that mess. We have all of our substitution methods, all of the identities, and all this stuff. So how about you think about this for about 3-4 minutes? Get together with someone else if you want to, and share ideas. Let's see if you can figure it out. Let's say you are taking an exam right now. Well, you can't collaborate on the exam, but you can say, huh? You can say, I understand this is tough. You're seeing it for the first time. Give it a week. I mean, week of practice, not just week of doing nothing. These things do not materialize out of nowhere. You just wake up one day, you know it all. Anyone figure it out? So we have 1/5, and we can put this into tangent theta over secant theta squared d theta, and then tangent is sine over cosine, secant is 1 over cosine, so it just becomes sine squared. So 1/5 integral of sine theta over cosine theta divided by 1 over cosine theta squared d theta. And then we cancel the cosines. And this is 1/5 integral of sine squared theta d theta. That's 1 over 10 integral of 1 minus cosine 2 theta d theta, which is 1 over 10 theta minus sine 2 theta over 2 plus c. Did we have limits on this one? No. We are not done because we have to work it out. Remember, we have 1 over 10 theta minus sine theta cosine theta plus c, because the formula would give you 2 and then we'll cancel the 2 in denominator. We had that situation already. So all I need to do now is to look these three up in the triangle and I'm done. So 1 over 10. Now for the theta, we can use inverse tangent of x over 5 from here. So inverse tangent x over 5 minus, now sine, we have to look at the triangle. Sine is opposite over hypotenuse, so that's x over square root of 25 plus x squared. And then I have to look up cosine. Cosine is 5 over the same square root. 5 over the same square root. It's 1 over 10. Tangent minus 1 x over 5. 5x over, and then square roots cancel, so just have 25 plus x squared plus c. There it is. Is this correct? No, you just take the derivative. It has to compress into what we have up there. If it doesn't, it's wrong. You start over. So all of these problems have the same pattern to create through the triangle, to go into trig subpart, and then after that use whatever method from trig integrals to integrate the problem. So let's do another one, because we can. Problem 63. Integral dx over x squared plus 6x plus 18. What now? Any ideas? What do we need to have? Perfect square. How do you get the perfect square out of this? Not the quadratic formula. There's a procedure called all the way back in intermediate algebra.
Is it completing the square?
Yes, completing the square. Have to do completing the square to get into the form of square of binomial or square root of binomial or something, and then you get to do the rest of the problem. So to complete the square on x squared plus 6x plus 18, b is equal to 6. We need b over 2 squared, which is 9. So we have x squared plus 6x plus 9 minus 9 plus 18. Square root of the first, sine of the second, square root of the third, and then finally plus by these two together create a 9. So now when you do this algebraic manipulation, you have x plus 3 squared plus 9. And you have it in a form that we need for our triangle. There's theta. These are legs. So here's your x plus 3, and here's your 3, and this is your square root of x plus 3 squared plus 9. So a little bit messier, but essentially the same as the previous problem. We have our red, we have our blue, and the steps must be the same as previous problem because you had the stuff that goes with the tangent, right? So tangent theta is x plus 3 over 3, from where x plus 3 is equal to 3 tangent theta, and x is equal to 3 tangent theta minus 3 d theta, dx is equal to 3 secant squared theta d theta. The minus 3 goes to 0, right? So that's the red. The blue is the cosine theta, which is 3 over the square root, from where the square root is equal to 3 over cosine theta, from where the square root is equal to 3 secant theta. Now, we don't need the square root, so we have to square both sides. Now, under the square root, you have this whole mess of x plus 3 squared plus 9. That's what underneath the root. So you have now the square will kill the root, and you just have x plus 3 squared plus 9 is 9 secant squared theta, and we just now plug everything in. So integral, instead of dx, I have 3 secant squared theta d theta divided by, and the entire denominator becomes 9 secant squared theta. Oh, look at this. 1/3 integral d theta. Awesome, right? Which is just 1/3 theta plus c, which is 1/3 inverse tangent of x plus 3 over 3 plus c. Well, that integral was a joke, right? Sometimes it turns out that way. Everything just cancels. So you have a secant squared, 1 over 3. So that was a joke to integrate. And I just pick random from the list. I didn't even plan on doing this problem. It's just said, let's do one completing the square. You look speechless. trig sum. It's like when you eat a spicy pepper, you just wait a little bit and it's better later. You have milk candy, right? Which is, you know, your trig. It's not that bad to begin with. Your trig identity. So all you need to do is to do a million problems. That's all. Now, you should, you know, try few problems in a trig integrals section, right? Maybe one of each kind. But then just do a million problems here, because every integral ends up in a trig integral, right? So you're necessarily practicing previous section. So you're practicing 2 sections for the price of 1. You know, it's like when you're buying a grabber on the infomercial, right? They say, if you call in the next 5 minutes, we will send you the second one. Really? You need 2? I guess if you drop 1, you can use the other one to pick this one up. And then, I don't know. I don't know why it's important to have 2, but or maybe you can gift that one to your friend. I don't know. We will include a free one. That just means that they are really overcharging for 1, right? Because if they can send you 2 for the price of 1 and still make profit, and pay for like an hour of infomercial there, tell you how awesome this thing is. You can pick apples. You can't reach because you have no ladder. Whatever. Anyway, that's the trig sub. As I mentioned, about 80 problems in the book to enjoy. And, you know, it does pop up here and there. But as a technique, I think it's cool. And probably Evan will go over some of these tomorrow as well if you ask. So it's time to start preparing seriously for the second exam, right? If you found the first exam tricky, you had only 2 methods of integration, basic and U sub, right? That's it on the first test. Second exam, 7 methods of integration plus improper integrals. It's a lot more variety than, you know. And then in some problems, you have to figure out which method to use, right? Is it by parts? Is it decomposition, right? It's just going to be a whole bunch of stuff. Now, obviously, the methods are different, just like the methods of the derivatives are different. You can differentiate very well whether you have to use chain rule, quotient rule, or product rule. Why? Because you have experience. Obviously, you don't have experience with this yet. You have to do insane amount of homework to gain that experience, and then you will be able to figure out which method to use. It's not just going to be there available just because you showed up to class, right? You have to work and figure it out. But it will be fine. Just keep practicing and don't let it sit. Don't let it say, okay, we just had a test. I can just rest for a week. Your week is 2.5 regular weeks. So don't mess around. All right, that's it.